Hello there, Mr. Sutton here, bringing you this lesson on the rectangular approximation method, or RAM, part 2. In this one, to follow up our first lesson, we're going to be determining whether a RAM method under or over approximates an integral, as well as converting between definite integrals and Riemann sums.
For your warm-up, see if you can complete this table saying whether each method, LRAM and RRAM, overestimates or underestimates an increasing function and a decreasing function. Pause the video and go for it. So for LRAM now, the easiest way to do this, by the way, is to draw a little picture. Here is left side approximation on an increasing function. Notice our left part of our rectangle is hitting the function. So the white space under here tells us that we have an underestimation going on. Now if we take the same method, left endpoint, and use a decreasing function, now that is causing us to overestimate the space under the curve. For RRAM, increasing function, the right endpoint is causing us to overestimate. And for a decreasing function, now we're hitting it too late and we're underestimating everything there. Let's use what we know about increasing and decreasing now to figure out if LRAM is going to underestimate or overestimate this integral. So first thing we need to do, we could graph this, but what if you don't have a grapher? And there's a faster way anyway. First thing we need to do is determine whether the function is increasing or decreasing on the interval that they gave us. And to do that, we need to figure out first the derivative of this. So pause the video and figure that out, and then find the critical values and all that. But don't do sign analysis just yet. All right, let's see if we're there. So derivative, that's going to be 4 times 1/4 is 1, x to the third, minus 12x squared plus 32x. Finding critical values now, we can take out an x from all this, and then we're going to need two things that multiply to positive 32 and add up to negative 12. That would be x minus 4 and x minus 8, with an x outside. So that we have the critical values then of 0, 4, and 8. Now, before you do sign analysis, we actually don't need to do sign analysis if the whole interval is on one part of this graph that our sign analysis would cover. So make sure that there's no critical values inside the interval, because that would mean we had a direction change. But if your interval is completely between critical values, then you can just test one value on your interval. So 5 to 7, that's between 4 and 8, so there's no direction changes in here. So let's just test a number between 5 and 7, like 6. If we plug 6 in to the derivative here, that's going to be a positive times a negative, so that whole thing will come out to less than 0, negative. That means we are decreasing on this interval. And you might remember from before, if you are decreasing, LRAM is going to overestimate that. So this one is overestimating. Now, a quick way of remembering, I have a silly way of remembering this. The way I think about it is LRAM is a pessimist. So when things are decreasing, when things are going downhill, LRAM's really happy about that and overestimates things. When things are increasing, LRAM gets kind of mad about that and underestimates. And RRAM's an optimist. RRAM's really happy when you're increasing and really sad when you're decreasing. So use whatever works, but that's what I use.
Let's change gears now and talk about Riemann sum notation and how this relates to definite integral notation. We can represent a Riemann sum that has n subintervals using sigma notation. So originally, when you were doing your RAM methods, which is basically what a Riemann sum is, you found the area under a curve by taking a bunch of rectangles, finding their bases, finding their heights, and adding all those different height base products together. But this is kind of a long-winded way of noting it. We can shorten that up considerably using our good Greek friend here, sigma, which basically just takes a bunch of these height times base things, and we have an index number for each of them, and it steps through all the index numbers from 1 to however many subintervals you want. So the height of all of these is actually the y values of your function f of x. So instead of writing h sub I, we can write f of x sub I. That gives us a specific function to plug the x values into. The base of all these rectangles is just going to be the change in your x values for this function. So we can rewrite this as sigma of f of x base I times delta x. So that's one way of noting Riemann sums. How do definite integrals relate to this? A definite integral, like this one down here, adds up an infinite number of super skinny rectangles between A and B. So with this Riemann sum notation, originally we only have a finite number of subintervals, but for this definite integral, we're saying this is what you would get if you split this up into a whole bunch of skinny rectangles. So we can actually convert this into Riemann sum notation if we make one small change to this. N is a finite number normally, so we actually need the limit as n approaches infinity of sigma of all of this stuff right here. So these two notations are equivalent, and in a moment we're going to be converting from one form into the other. One thing worth noting before we move on, though, and that's that this f of x here, this is kind of a very big picture idea. This f of x actually represents all the heights of an infinite number of super skinny rectangles that you're chopping your area into. And this little dx, that a lot of people don't know what it actually means, this is actually corresponding to this delta x over here. This is the infinitely small base of all those infinite number of rectangles. At this point, we're going to learn how to express an integral, like this one, as a Riemann sum, something in this format here. The key to doing this, since this format really only has n's and i's that you're allowed to plug things into, we need to express everything in terms of I and n. And the first step to doing that is to figure out what delta x is. Why? Because we're going to use this delta x to figure out all the other pieces of this. So we start here. So delta x, that is the length of the base of your rectangles that you're breaking this up into. To find out the length of these rectangles, we need to first figure out how much overall space we have to work with, which is going to be your interval length from your lower limit of integration to your upper limit of integration. And then we just need to divide that by the number of rectangles. How many rectangles do we have here? Oh, n. This is all about splitting up your curve into an infinite number of rectangles. So we just need to do b minus a over n, and that'll give you your delta x. Now, we're not actually supposed to plug something in for n, but b and a, that's just 3 minus 1, so we can say delta x is going to be 2 over n. All right, now that we've got that piece of it, let's move on to figuring out x sub I. Now, the key to expressing x sub I is to realize that what this is, if you were doing, for example, a right Riemann sum, a right rectangular approximation, this x sub I, that would basically be the endpoint, the right endpoint of all your rectangles. Now remember, when we were just doing normal RAM, RRAM, you were taking that right endpoint and plugging it into the function to get the height of the rectangles. So we need to figure out how to express all those x values. So if we were doing this using this interval here, our very first x value would be, well, your left endpoint of your first rectangle would be the a value here, 1, because that's where everything is beginning for the x values. But then to get the right endpoint of that rectangle, you would have to add the subinterval length. What's the subinterval length again? Oh yeah, that's this delta x, this 2 over n. So to get the very first xi, you would have to do a plus delta x. But if you want to get the ith right endpoint, then instead of doing a plus just 1 delta x, you're going to have to do a plus I delta x's. We know what the a value is. That's the 1 over here. We know what delta x is. That's the 2 over n. So we can actually write this as 1 plus 2i over n. So that's honestly, I think, the most difficult piece to get. Once we have this, we just have to apply the function to x sub I and then eventually substitute back in for the delta x. So I'm going to do this in 2 steps. First off, instead of writing this sigma notation with f of xi, I'm going to actually use the function from the integrand in my sigma notation. So I'm going to rewrite this with 2x sub I plus 1. I didn't change anything else at all, but now I am going to substitute in for delta x and x sub I. So I can write this as 2 parentheses, all this stuff here, 1 plus 2i over n. Don't forget a plus 1 after that parentheses. And then we have to plug in 2 over n for delta x. So I'm going to display it, and then I'll go through it one more time. So we've got 2 x sub I, that's this red stuff here. We have the plus 1. That's all in a big parentheses. And then outside of that, we have delta x, which again was 2 over n. So the bad news is this is kind of a confusing process at first that you might have to do several times before you truly get the hang of it. The good news is when you do get the hang of it, it actually is not that long of a process. So pause the video and see how far you can get on this one, converting this into a Riemann sum. All right, let's see how we did. So here's our Riemann sum notation that we're going to turn everything into. And we're going to find delta x first. So that's going to be b minus a over n. So in this case, 2 minus negative 1 over n. That's 2 plus 1 over n, so 3n. Next, remember the x sub I is going to be a plus I delta x. So in this case, our a value is negative 1, and I stays I. Delta x we just found to be 3 over n. So this is going to be negative 1 plus 3i over n. And now I'm going to plug everything in and apply the function. Now the function itself is cubing, so I'm going to have Riemann sum here of negative 1 plus 3i over n quantity cubed times my delta x value of 3 over n. And that's it. See, that wasn't too bad. You just have to get used to it. Now that we've converted definite integrals into Riemann sums, let's see if we can convert a Riemann sum into a definite integral. So we're given something in this crazy-looking form, and if this is the first time you've ever seen one of these, then you're probably very intimidated. Hopefully the first time's not on the actual AP test. This is the cute little form we're trying to turn all of that into. So a few things we're going to need for this. We need the a, we need the b, and we need a function to use instead of f of x. Let's start with the a value. The a value is just going to be whatever the number is that's being added to the fraction that has the I and the n. If you've actually built a Riemann sum out of a definite integral already, then you know where this negative 2 is coming from. This is the a value from the original definite integral. So our a value then here is going to be negative 2. Next, we need the b value, but in order to get from a to b, we need to know the length of the interval. Then we could just add it to the a value. To find the interval length, remember, that's the thing that's being divided by n over here. This little 2 over n bit is really delta x. So to find the actual interval length, you just have to figure out what you're dividing by n. So now that we know that 2 is our interval length, we just have to add that to a. And that'll give us the b value. So we're going to have negative 2 plus 2, which gives us a b value of 0. All we need now is the actual function that we have to replace f of x with. So in addition to subbing in negative 2 for a and 0 for b, we're going to replace f of x with, well, let's see here. We have a bunch of stuff being squared and multiplied by 3. So that's 3x squared. And we have some stuff being multiplied by 2, the same stuff, so that's 2x. So we have integral from negative 2 to 0 of 3x squared plus 2x dx. And if you have an integrand that has multiple terms in it, then you do need to put all of that in a parentheses. Here's another Riemann sum to definite integral problem. Pause the video and try this one out on your own. So here's our definite integral form. A value, that's the thing that's being added to the I over n term. Now in this case, you're like, well, wait a sec. Nothing's being added to that inside that parentheses. And you're right. We have an a value of 0. Every now and then that happens, and that's okay. To get the b value now, we need to figure out the interval length and add that to the a value of 0. So again, for interval length, we look out here to this term with the n in the denominator. Now you have to be careful here because we're asking what is being divided by n. And in this case, this is like having pi over 6 over n. Even though the 6 is in the denominator, you can think of this as pi over 6 being divided by n. So we're just doing 0 plus pi over 6, which is, of course, pi over 6. What's the function that we're going to replace f of x with? So that's the thing that is being applied to the a plus I delta x. And in this case, all that I over n stuff is inside of the tan function. So our function here is just going to be tangent of x. So we've got the interval from 0 to pi over 6 of tan x. That's it for this lesson on Riemann sums and definite integrals. Until next time, this is Mr. Sutton, signing off.